Hi everybody. So in this video we're going to be talking about algebra and function basics, still part of chapter 1. Specifically, we're going to be covering inverse functions, and the first part of that is pairs of inverse functions. So how do we know if two functions are the inverse of each other? So let's suppose we have a function g and a function f. So we know that they are the inverse of each other if the composition of g of f of x will give us x as a result, and if the composition of f of g of x will also give x as a result. So we have this condition and this condition, then we know that g and f are inverse of each other. There's another aspect of this that is very interesting, and let's suppose we have f up here. You know that for x we will be getting a y value. X is the domain of f, and y represents part of the range. So the x values are the domain of f, and the y values would be the range. For the inverse, it would be the opposite of that, or the inverse of that. The domain of the inverse would be the range of the original function f. So the domain, the range of f becomes the domain of the inverse. And then the domain of f will become the range of the inverse. So now let's take a look at example 1.17. And they give us two functions, and they want us to show that these functions h and p are inverse functions. So that means that we have to do the composition of each other, right? So first let's start with h of p of x. And this is going to equal plugging in this function inside here, right? So that's going to be 2x plus 3, this instead of x in h of x, minus 3 divided by 2. So notice that this is going to give us x because this and this cancel out, and then we're going to be left with 2x over 2, and that's just going to equal x. So the first condition is there, but we also have to test for the other way around. So we have to do p of h of x. And then we're going to have to plug in h of x into p of x. So that's going to be 2 times x minus 3 over 2 plus 3. And this also is obviously going to give us x. As you can see, this and this will cancel out. And then we're going to be left with minus 3 plus 3. And finally, there's only x. Therefore, h and p are inverse functions. Okay, so in this next slide, we're going to talk about the existence of an inverse function. So does a function have an inverse? So let's take the case of f of x equals x squared. Now notice that if we pick some values for x, let's say 2, negative 2, 3, and negative 3. So this would be the domain we're going to be testing. And of course, we have to map this through x squared, and that's going to give us f of x. So what happens when we plug in 2? If we plug in 2 into x squared, we're going to get the number 4. So 2 maps into 4. But what happens if we plug in negative 2? Well, negative 2 squared is also 4, so that also maps to 4. 3 squared would equal 9, but then also negative 3 would equal 9. So this means that this function is what's called a many to 1. So if we map x into x squared, this function f of x is a many to 1 function. So what would happen with the inverse of this? The inverse of this makes this go backwards, right? This would now be the new domain. This would be the domain of the inverse. So if this is the inverse here, this would be the domain, or the x values, and this would be the range. But what happens to the domain in relation to the range? Well, this would now become a one-to-many relation. This would not be a function. This would be a relation. Because many to one can be a function. That's allowed. But a one-to-many would not be a function of y in terms of x. So that means that x squared itself does not have an inverse. In general, we know that a function does not have an inverse if we do something called the horizontal line test. So if we draw a horizontal line through the graph of a function and it intercepts the function more than once, as it does here, then it would not have an inverse. But what can we do in order for this to have an inverse? Well, we can restrict the domain. So notice that in figure 1.23, the domain of x squared is restricted for values or for a domain of x greater than or equal to 0. And in result, we have this curve and this partial parabola, right? This would be half of the parabola. This would have an inverse because it would pass the horizontal line test no matter where you draw horizontal lines. Or also, on the other hand, you can restrict the domain to all x values that are less than or equal to 0, and this would also have an inverse because, as you can see, it easily passes the horizontal line test. Now we're going to learn how to find the inverse of a function. We're going to start with example 1.18. And it says the function f is defined for x belonging to all the reals by f of x equals 4x minus 8. Part A. Determine if f has an inverse. If not, restrict the domain of f in order to find an inverse function. So notice that the domain of this is all real numbers, and because it's a line, it definitely has an inverse. This would pass the horizontal line test anywhere. So this definitely has an inverse. We don't have to restrict the domain. So what would be the inverse? Since we have that f of x is equal to 4x minus 8, we can rewrite this by saying that 4x minus 8 is equal to y. So in order to find an inverse, what we do is that we swap the x with the y. So we would rewrite this as 4y minus 8 equals x, and then solve for y. So we're going to get that y is equal to x plus 8 over 4. So this would be the inverse function of f. So notice that this is not pronounced f to the minus 1 because f to the minus 1 is 1 over f. So this is not how you say this. This is just called inverse function. Okay, so now let's go to part B. So for part B, they want us to verify the result by showing that f of the inverse of f equals x and that the inverse of f, composition f, equals x. So that is just a test that we talked about before. So let's start with f of, well, first of all, let's remember that the inverse that we got, the inverse of f was y or x plus 8 divided by 4. Okay, so now for part B, we're going to do the composition of f with its inverse. In other words, plug in the inverse into f of x. So this is going to be 4 times x plus 8 divided by 4 minus 8. And this is obviously going to give us x, because this will cancel out with this, and this will cancel out with that, and we have x remaining. Now we have to do the opposite, so we're going to do the composition of the inverse of f with f, and that means plugging in f in its inverse. So that would give us 4x minus 8 plus 8 divided by 4. And this is also obviously going to give us x. How so? Well, first we can add this, and that gives us 0. And then 4 divided by 4 is 1, and we end up with x. So this verifies the result. Okay, and finally for part C, they ask us to graph f and its inverse function on the same set of axes. Okay, so we know that f of x is equal to 4x minus 8, and its inverse is x plus 8 over 4. So we're going to graph these on the same set of axes. Okay, so it's just going to be a quick sketch. So let's do this one first. Notice that it's 4x minus 8. That means that this is the y-intercept minus 8. So let's count negative 8. 1, 2, 3, 4, 5, 6, 7, 8. So this would be negative 8. It would go through here. That would be the y-intercept. What would be the x-intercept? The x-intercept would be the solution of this equal to 0. And that's easy to see that it's 2. So it goes through 2. Therefore, and I'm going to try to draw this as best as I can, guys. Excuse my drawing here. So we have to draw this carefully. Oh, it's supposed to be a straight line. And there we are. Okay, so that would be the graph of f. And now to do the inverse, I'm not even going to do calculations. Why not? Well, because if we just swap x and y, notice that if x was 2 for f of x, then for the inverse, y is going to be 2. So it's going to go through y equals 2. And that would be its y-intercept. You can clearly see that because if you divide 8 by 4, that equals 2. And then it's also going to go through negative 8 because now that would be the x-intercept. So 1, 2, 3, 4, 5, 6, 7, 8. So it goes through negative 8 for x and through 2 for y. And I'm going to try to make a drawing here as best as I can. So let's go. Okay, that's not too bad. Not too bad. Okay, so that would be those two graphed on the same set of axes. Now notice that if I draw a line for y equals x, it should go right between them, as you can see, and they would be a reflection of each other across the identity function y equals x. So this would be y equals x. And notice that they reflect each other across that line. Next, let's take a look at example 1.19. And they say, consider the function f such that x maps into square root of x plus 3, x greater than or equal to negative 3. So they already give us a restricted domain, which makes sense because it's a square root. So the domain would be restricted to values that are greater than or equal to negative 3. A, determine the inverse function. Okay, so for that, we do the same as usual. We say, okay, square root of x plus 3 equals y. Exchange y and x. So we're going to go square root of y plus 3 is equal to x. In this case, we square both sides. So we get that y plus 3 is equal to x squared. Therefore, y is equal to x squared minus 3. But this is the inverse of f of x. So we write that as inverse of f of x is equal to x squared minus 3. Okay, for part B, they want us to find the domain of the inverse. So if you look at the inverse, right, the inverse is x squared minus 3. We might be tempted to say that the domain of this is R, but that would be false. The domain of this would be the range of f of x. So what's the range of f of x? Since the lowest value is negative 3, and after that it just goes up and up and up, that means that the range would be from 0 to infinity. Therefore, the domain of the inverse would be the range of f of x. So that means that the domain of this would be restricted to 0 to infinity. And we finish this video by taking a look at example 1.20. And it says, consider the functions f of x equals 2 times x plus 4, and g of x is equal to 1 minus x over 3. Find the inverse of g and state its domain and range. So this is the same as usual. right? We say 1 minus x over 3 is equal to y. Exchange y and x, I'm going to get that 1 minus y over 3 is equal to x. Therefore, 1 minus y is equal to 3x. Then minus y is equal to 3x minus 1. Therefore, y is equal to 1 minus 3x. And this is the inverse of g, so we have to write it properly. Inverse of g equals 1 minus 3x. State its domain and range. Well, notice that g of x does not have any restrictions on the domain. So the domain would be R for g of x, and the range would also be R. Therefore, for its inverse, you have the same situation. Then we have that the domain would be x belongs to all reals, and the range would be y belongs to all reals. Okay, so for part B, they ask us to solve the following equation. It says f composition inverse of g is equal to 2. So let's remember that the inverse that we found, right? The inverse of g, we said is 1 minus 3x. So we need this. We have to plug that into f. So if we plug that into f, we're going to get 2 times 1 minus 3x, which we substitute for x, plus 4 is equal to 2. So notice that this 2 is multiplying, therefore I can send it to divide, and I'm going to get that these cancel out, and this would be 1 now. So I'm going to get that 1 minus 3x plus 4 is equal to 1. That means that minus 3x plus 5 is equal to 1. Therefore, minus 3x is equal to minus 4. And then x would equal 4/3, and that would be the solution.